Thank you. I'm very happy to join the MLT session today. And today I'm going to introduce one of our recent work, which is called Rethinking Importance Weighting for Deep Learning and Distribution Shift. So this is a joint work with Tongtong Fang, Gang Niu, Masashi Sugiyama, and my name is Nan Lu. Maybe today's presentation may not have a lot of visualizations because the main purpose of this paper is to propose effective algorithm for learning under distribution shift. So I may try my best to introduce the idea and the algorithm of this paper. So first, I will give you a brief introduction about myself. So my name is Nan Lu, and I'm a PhD student at University of Tokyo. My research interests mainly lie in the weakly supervised learning part, which includes of positive and labeled classification, where we want to train a classifier from only positive and unlabeled data, and also unlabeled and labeled classification, where we want to train classifiers from only sets of unlabeled data, only unlabeled data bags. And also my research interest lie in learning under distribution shift, which is the topic, the focus of today's presentation. And also I have broad interest in deep learning and privacy preserving learning. So next I will introduce this paper. So first let's talk about the motivations. So I'm not sure if all of you have studied the hot research question distribution shift, because nowadays the supervised deep learning has been very successful, but learning under distribution shift is a very big challenge. Let's say in autonomous driving, if you train an autonomous car in the good weather, we also need the car to work well in the bad weather, right? So here, maybe the training data are all collected from the good weather, such as a sunny day, but the test data may include some rainy day or rainstorm day. So we need our model or car to work well from both training and test data. But in the real world, there are a lot of distribution shift scenarios which shows that the probability distribution of the training data differs from the probability distribution of the test data. So here we use this joint distribution to show this distribution shift, which means the joint distribution of the training data is different from the joint distribution of the test data. This is a very big challenge for nowadays supervised deep learning. Next, I will introduce a few distribution shift scenarios. So the first one is called covariance shift, which means the marginal distribution PX shifts from training to test. For example, if you use a deep neural network to train a classifier, so here we can see the blue line shows the training distribution and the training density, and the black line shows the test density. So if you use a deep neural network to train such data, if you use, it will focus more on the training data, but less on the test data. So it may not work very well on the test data. And also there are many cases which is called class pair shift, where the class pair, which is the proportion of the class proportions, shifts from training to test. So for example, in this figure, we can see there are more cats and less dogs, but in the test data, maybe we can have equal number of cats and dogs. So this kind of imbalanced data is also a challenge. And another example may be the label noise case, which means in this figure, we can see these are some training data. We can see there are some noisy labels. Maybe for this figure, this is a cat, but we label it wrongly as dog. And for this figure, we also have noisy labels, because nowadays we really have a large amount of training data. And so it is often the case that there are some noisy labels included in the training data. So if you don't deal with such a distribution shift, maybe our test performance maybe our model will overfit to the noisy labels and may not work well on the test data. So to deal with such distribution shift problems, in recent years, more than 200 top conference papers have been published in the last 2 decades. And I also refer the readers to check this very good textbooks that is on distribution shift to learn more about this interesting research topic. A traditional method, a powerful tool to deal with the distribution shift is called importance weighting. So importance weighting always has, importance weighting often have two steps. So in the first step, we estimate the weight, which is also a density ratio, which is the test over training density ratio. We call it importance and denote it by W star. And the second step is weighted classification, where we use the importance weights to weight the loss of to weight the training losses, so that after the weighting, the expectation. So after weighting, we can obtain this formula. So here, the XY data, the data XY are drawn from the training distribution, and after weighting, it is equal to this term, where the XY data are drawn from the test distribution. So importance weighting is a traditional method to deal with such distribution shift, and our learning objective, which use sample means to estimate this term, can be seen as an unbiased estimator of the original test risk. So this method is consistent and work very well in the non-deep learning error. And the goal of this paper is because importance weighting is a common practice for non-deep learning and the distribution shift, but it cannot very well on complex data. So here we show some experimental results. The left figure shows the experimental result of importance weighting on easier data set, fashion MNIST. So here the green line is the test accuracy of importance weighting, and the pink one shows we only use 1,000 training data, the clean training data without any distribution shift. The performance of this clean baseline method, we can see in this easy data set, the importance weighting method perform better than the clean baseline. But if we use a more difficult data set, which is CFR10 here, we can see the importance weighting method performs similarly to this small clean baseline method. So the goal, especially in the deep learning error. So next, I will introduce the proposed method. So let's rethink the traditional importance weighting method, which has two steps. The first step is to estimate the weight, which is a density ratio. And the second step is to do weighted classification, which is in this way. And we found that the problem that why importance weighting cannot work well in deep learning is because that if you are given very difficult high-dimensional training data X, then it is very difficult to boost the expressive power of the weight estimation here, because nowadays most deep neural network models are very hard to train with this density ratio estimation objective, but those models are proposed to deal with more general objectives, such as a classification. So our idea is to, our idea may be, can we boost the weight estimation step by using an external feature extractor? So first, our idea is to boost an external feature extractor inside this deep classifier F, but it will cause a dilemma here. So let's remember that if we want to estimate the importance weight, we want to boost it by using a feature extractor here. But if we want to train a feature extractor here, we need to train a classifier F, right? And then we cut off the linear classifier layer here, and then we obtain this extractor. So this causes the dilemma that if we want a good weight W, we need a good feature extractor, and this needs a good classifier F. And if we need a good classifier F, we also need a good estimation of weight. So this causes a chicken or egg problem. How to solve this problem? Our idea is to boost the expressive power of weight estimation by a feature extractor from this deep classifier F. So in this way, we can use a deep classifier. So we can use the deep classifier to induce a feature extractor here, and we can use this feature extractor to train an importance weight. So and we also show that in the paper, we also show that if we show that the we also show this nonlinear transformation of data theorem. So if we can, so for fixed deterministic and invertible transformation pi here, and we can let PTR of Z and PT of Z be the probability density functions induced by the training and test joint distribution and our transformation pi. And we can obtain that this W star shows the optimal weights, and this W star Z shows the weights estimated from the transformed data. So if if the transformation is part of the classifier F, then the classifier must be a reasonably good classifier, so that the transformation pi compresses this data back to the manifold. This is the interpretation of this theorem. And let's show a very detailed diagram of the proposed method, which we call dynamic importance weighting. So this is an end-to-end solution. So here we can see this as a training and validation data. And then we use the feature extractor, which is short for FE here, and linear classifier, which is short for LC here. And those two terms form form the deep classifier here. And then we use this feature extractor to transform the training data and validation data, which are shown here, train data transformed and validation data transformed. And then we estimate the weights on those transformed training and validation data. And then we use these estimated weights to reweight the training losses. And then we update, and then we use this weighted loss to update our deep classifier. And then after this updation, our feature extractor can also be updated. So this is a dynamic method to apply importance weighting. So let me repeat it again. So we train a deep classifier from the weighted training data here, and create a feature extractor FE from our deep classifier here. And in the meanwhile, we perform weight estimation on the data transformed from this feature extractor in a seamless manner. So here, the weight is estimated from the transformed training and validation data. And we use circular update to update the deep classifier, which is also the feature extractor. If we use this method, we can do the importance weighting in a single step, which is totally different from the traditional methods, which need two separate steps. So here is the algorithm of the dynamic importance weighting, which is shown in a mini batch. So we require a training mini batch, a training data mini batch, and a validation data mini batch. And the current deep classifier model is denoted as F here. So we propose two implementations. The first one is hidden layer output transformation version, where we forward the input data, the training and validation mini batches, and then we retrieve the hidden layer outputs, which are ZTR and ZV show the transformed training and validation data. And then we partition those transformed data using their labels. So we partition them into K parts. We partition each of them into K parts, and for each class, we match those transformed data to obtain their weights, and then we multiply the weights, and then we multiply all the weights. After calculating these weights, we can compute the loss values for the training data. And we can use the weighted empirical risk to do the backward propagation, to calculate the gradient and do backward propagation, and then update our deep classifier theta here. And because the deep classifier theta is updated, our feature extractor inside this classifier is also updated. So this is a dynamic solution here. And we propose another implementation, which is called loss value transformation. And first, we also forward the input data, the input training and the validation batch, and then we compute the loss values of them, which are shown as LTR and LV. And then we match, and here, instead of calculating the importance weights of the data, of the transformed data, here we match the loss LTR, the training loss and the validation loss to obtain the weights. And then we use this weight to weight the training losses. And then we can use the weighted objective to calculate the gradients and do backward propagation. And then here we can also update, after backward propagation, we update the classifier theta here, and we can also update the feature extractor inside this classifier. So these two implementations all work well in our experiments, and we have shown that the loss value transformation version is more easier to implement, and the performance is better. So here we can give more detailed explanations of the hidden layer output transformation. So first we estimate the weight, PTY over PTRY. And then we partition the training and validation data according to their labels. And then we invoke the weight estimation k times on the k partitions, which is shown in this way. So this is the density ratio, and we can decompose it in this way. And by applying this weight WY star, and we can obtain this. For the loss value transformation, we find a set of weights W such that for the training losses, we can use this formula satisfies, which means this is a validation loss here. This is a validation loss here, and this is the training loss. After weighting, in each mini batch, the training loss is approximately equal to the validation loss. And then the last question is how to estimate the weight. And in this paper, we employ kernel mean matching, which minimizes the mean discrepancy of the training and validation data in an RKHS. So this is a learning objective. So this is an objective of kernel mean matching, and we minimize this subject to these two constraints. And in traditional importance weighting, kernel mean matching is performed on all the training data within one class, and in our dynamic importance weighting, the kernel mean matching is performed on transformed data in every mini batch, because the data are already transformed from the feature extractor in our method. So it can be very low dimensional, and kernel mean matching can achieve better performance. The estimated weights can be more meaningful. And finally, let's take a look at the experiments. So first, we share some experimental results on label noise setting. So the setting is that the PX, the marginal distribution, the marginal density PX is the same from training to test, but the posterior P of Y given X changes from training to test, and we use the dynamic importance weighting method to solve this kind of distribution shift. And here are some experimental results on CIFAR10 dataset. And here we use different shift settings for this label noise, for simulating this label noise. So here 0.3 means there are 30% of the labels are corrupted. So which means the noise rate is 0.3, and in this figure the noise rate is 0.4, and in this figure the noise rate is 0.5. And we can see our proposed method, which is shown in the blue line. It performs better than the baseline methods in all settings. So this demonstrates the effectiveness of dynamic importance weighting. Especially, we can take a look at the traditional method, importance weighting in the blue line. Our method improves the traditional two-step importance weighting method to a large extent. And also, in this slide, I show the weight the statistics of weight distributions on CIFAR10, so here we can see this histogram plots. These weights are estimated by our method. We can see our method. This blue the green shows the mislabeled data, and the orange color shows the intact data. We can see if we use our dynamic importance weighting method for those mislabeled data, we can assign very small weights, which are approximately 0 to those data. And for those intact data, which has correct labels, we can assign larger weights to them. So this benefits training. And for some baseline methods, this is the traditional importance weighting method. It cannot distinguish the good data, which are intact data, which have the correct labels, and the bad data, which are mislabeled data, which have some noisy labels. So the traditional importance weighting method cannot distinguish them. It assigns small weights and also random. And for another base method, which is called reweight, the performance is also not very good. But our method can distinguish those good and bad data and assign larger and smaller weights to them. And there are many more experiments in the paper. So we also conduct label noise experiments on other benchmark data sets, FreshMNIST and CFR100. And in the paper, we also provide some class pair shift experiments on FreshMNIST. And we also conduct some ablation studies, because for our proposed dynamic importance weighting method, we have a lot of options to design this. For example, we can choose whether we update this feature extractor or we only pre-train this feature extractor. And also we have different choices of data transformation. In the algorithm part, we have proposed one hidden layer transformation and another loss value transformation. And in the paper, we also show the denoising effects of the proposed dynamic importance weighting method. So finally, I will briefly summarize today's presentation. For deep learning under distribution shift, the traditional method importance weighting may suffer from a circular dependency if we want to boost the expressive power of the weight estimation step. To avoid this issue, we propose dynamic importance weighting, which is an end-to-end solution. So our first contribution is we introduce feature extractors, which is inside the deep classifier. And then we embed importance weighting in every mini batch for training the classifier. And there are many algorithm design options to make dynamic importance, to make your own dynamic importance weighting. Yeah, thanks for your attention. If you have any questions, maybe you can discuss in the following Q&A session.
Thank you very much, Nan. This is a very intense and very compact and informative session. No, thank you.
Thank you. Yeah, because the paper is very contains a lot of equations. Maybe you can go through each part in this Q&A session in more detail.
Right. Yes. Yeah. So to proceed, I would like to maybe you can correct me, please. I would like to summarize a bit in a high level.
Yeah, sure.
Yeah, for our audience, so that we can move forward. First, terminologies. Distribution shift. I'm thinking this is a more general idea for. I'm commonly hearing like concept drift, data drift, like in when people
it's
are
related.
Yes. This is the more general term. This is the basically all kinds of drifts are under this distribution shift. Is that correct?
Yes. Distribution shift is a very general concept, because it refers to the training data. Distribution differs from the test one.
Yes. So everything with that is called distribution shift. Okay, so that's why we have all this covariance shift. Different kinds.
Yes. There are different kinds of distribution shift.
Right. Then my next comment would be, I think this also would be very helpful in dealing with fairness.
Yes.
Right?
For example, in this kind of imbalanced data.
Right.
If we don't deal with it, it will cause some fairness issues.
Right. Yes, so that's why I really like your topic. Another point, maybe a high level point I want to point out is that so currently these kinds of problems, people are aware, many groups are aware, and one thing that I've heard trying to do this is using what they call ML ops, basically a batch of practices in production in industry that tries to solve this problem in different, in a full production environment, like improving the data collection, improving the data monitoring, and that kind of things, right? But you are proposing something which is which could be done in a single algorithm, ideally, and could potentially already be helpful in those kinds of problems being tackled by MLOps, such as fairness and the likes, right? So I think it's a quite powerful and important work. Am I at least partly correct?
Yeah. Actually, I think in the industry, maybe people solve this kind of distribution shift problem by improving their data collection. Maybe they want to, for example, for this kind of covariance shift, maybe people can work much harder on collecting much better training data that is more similar to the test data. And also for this classifier shift, it is also similar. People may collect a lot of minority classes to make it more equal or more like the test data. But our method is propose another solution that estimates the weights of this test over training density ratio, and then by applying this kind of weighted classification, we can train our method just using this shifted training data. It is an alternative method, alternative solution.
Yes, that's why I find it very promising, because let's go back to that page. Yes, around there. So as you said, if it's in production, you can improve it somehow, but costs money, right? Costs a lot of money. And this is the idea. This is an algorithm. So if you can implement it, won't cost you as much, if this is correct.
Yeah, the high level idea for this paper is because importance weighting is the common practice for non-deep learning, because in the non-deep learning area, the data are very simple. The X is very low dimensional, but nowadays our data are very complex and high dimensional. So to estimate this density ratio can be very difficult in nowadays.
I see.
Yeah, so we propose a dynamic method to boost this weight estimation step by using a feature extractor that is inside our classifier. Yeah, this is a key idea of this paper.
Now I have a technical question. Are you trying to make W star close to 1?
Oh, no, actually no, because here you can see this figure. So this figure shows the distribution of the weights. This is our method. You can see the green color shows the mislabeled data, which should be treated as bad data because their labels are mislabeled, because their labels are not correct. And this orange color shows the weight distribution of the intact data. Their labels are correct. So our method can assign small weights to the bad data and larger weights to the good data. So it's a reweighting. So this is a reweighting idea.
I see. Okay. Yeah. I kind of misunderstood the goal there. So just the goal is that if you go back to that page, you just want the full expected value to be 1. Yeah, not necessarily.
Not necessarily to be 1, because here's the distribution.
Right. Yeah, it's a difference. Now I noticed.
Yeah. The training and the test, the distribution are different. Yeah, this is the interesting part.
Yes, they're different distributions.
Yeah, so here actually the weights plays a very important role in this equation.
I mistakenly said, I see your goal to make it 1. Yeah, it's not correct. Okay,
it's not correct. Thank you for your questions.